Hello. Hello. Thank you. I'd like to.
नमस्कार। थोड़ी सी देरी के लिए स्टार्ट होने के लिए क्षमा। आप सभी का स्वागत, अभिनंदन, आदाबर्स, केम छो, राधे राधे, अम्बागाड़ी, राम राम एंड वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के 82वें पीआरएल के अमृत व्याख्यान में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज very warmly welcome you all for 82nd PRL का अमृत व्याख्यान। PRL established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, has completed its 75 years of existence. And as we celebrate PRL's independence of 75 years, we are also celebrating PRL's platinum jubilee. And in this celebration, we have started the series of PRL Amrit Vyakhyaan, which started on 4th of August 2021, and we completed 75 episodes consecutively every Wednesday at 4 p.m. This legacy is continuing, and from 30th of January this year, after we completed the 75 episodes, we started the PRL Amrit Vyakhyaan 2.0, where we have every month one time. So today, that is 19th of July, Wednesday, 2023 at 4 p.m., we have yet another very distinguished Vyakhyaan with us, who is going to give the 82nd Vyakhyaan. And he is none other than Professor Mark Baskaran, who is a professor and chair, Department of Environmental Science and Geology at Wayne State University in Detroit, Michigan, USA. And he's going to speak to us on the topic, human impact on global climate change over the past 2 centuries using isotope-tracing technique. This topic is, of course, very apt because climate change, and particularly global climate change, is the buzzword today. And we are extremely delighted to have Professor Mark Baskaran with us today in person to deliver this Vyakhyaan. Without taking much time, I would now request my colleague, Professor R.D. Deshpande, to kindly introduce today's Vyakhyaan and to the audience here, as well as to the audience who are live watching us on PRL's YouTube channel. Thank you, Dhanyavad, and over to you, Professor Deshpande.
Thank you very much, Dr. Bhardwaj, for your welcome remarks and giving me this opportunity to introduce today's speaker. It's an honor and privilege for me to introduce the distinguished speaker for today's 82nd PRL Amrut Vyakhyaan, Professor Mark Baskaran, who is an internationally acclaimed scholar in the field of environmental science and geochemistry. He is well known world over for his seminal contributions in applications of isotopes as tracers and chronometers to study environmental subsystems. It is highly prestigious for all of us and all the more important that this great scholar is a PRL alumnus who submitted his PhD thesis in 1985 entitled Radiometric, Mineralogical and Trace Elemental Studies of the Saurashtra Quaternary Carbonate Deposits, Implications to their Age and Origin. So this thesis marks number 141 in the chronology of the thesis so far submitted. Well, I'll try to walk you through very briefly the bio sketch of Professor Baskaran. He did his MSc in physics from Madurai Kamaraj University in 1979. Then he moved to PRL and he worked here and submitted his PhD from Gujarat University and PRL in 1985, as I mentioned. Thereafter, in 87, he moved to University of Alaska at Fairbanks, where he worked for over a year. And then he moved to Texas A&M University at Galveston in 1988. Thereafter, he joined Wayne State University, Detroit in 1999, after about 10 years of research at Texas. And then he got his tenure in 2004 and became a tenured full professor in 2007. I vividly remember that Professor Mark was here in 2007 and he delivered a lecture in Geosciences Division. In terms of publication records, based on his research focus on applications of isotopes as tracers and chronometers, he has published 160 journal articles. And for an experimental geologist who has to, work in the crews and the field, 160 publications is indeed a remarkable number. He has edited 2 volumes of handbooks of environmental isotopes geochemistry in 2011, and he has written a well-known monograph on radon, a tracer for geological, geophysical, and geochemical studies. I think many of the geology students would have read these things. He has, as on today, 10,498 citations with an impressive H index of 61. In terms of awards, there's a long list. I'll just run through briefly. His Wayne State University Board of Governors Distinguished Faculty Fellow Award in 2010-11, Board of Governors Faculty Recognition Award in 2013, Distinguished Graduate Mentor Award, Senior Fulbright Scholar Award in 2015. He was elected to the American Geophysical Union Honors and Recognition Committee in 2022. He was WSU's Academy of Scholars recipient, which is actually a lifetime appointment. He was inaugural chair of the AGU's Devendra Lal Memorial Medal Selection Committee. We know that one of our colleagues is a recipient of this, and so far 5 Indians have received this award. He is member of the US National Fulbright Screening Committee. He has been a consultant for IAEA Vienna, Monaco, US Geological Survey, and Sandia National Laboratory. He has been a distinguished visiting professor at East China Normal University. He has lectured around the globe and delivered more than 60 invited talks in different parts of the world. And since 2018, he's serving as the chair of the Department of Environmental Sciences and Geology at Wayne State University. So with these words, and on behalf of all of us, I warmly invite Professor Baskaran to deliver his talk. Please give a big hand clap.
Professor Bhardwaj, distinct administrative, senior administrative officers, faculty and staff, students. It's my honor and privilege to come back to this place once I was one of you like this. And now, because what training I got here that led me to travel to start of one place when someone else was paying for it. And enjoyed so much of research going to different parts of the earth. I was particularly so excited to see Professor Kumar Bhatt, who taught us quantum mechanics in 1979 when I joined as a student. And another person is Dr. Rangarajan is here. We were sitting next to each other almost most of the time when I was in here as a student. And he joined, I think, 2-3 months after me. Apart from that, we come to a place where people can ask you who you are. Who are you? Yeah, you know. But it's a real joy for me to see the students, especially, that they are going to be the leaders. They are going to be playing the science industry in this country. There are many things I can keep talking about that, but simply state that PRL has left a mark in the world, that all kinds of comments, people whom most of you might know, through the work of their postdoctoral fellowship in different parts of the world, and then saying that, oh, you are from this group. Oh, yeah, we know that, kind of. So I think that's a testament to the quality of education, that quality of training that is there, that has prepared to go in many parts of the world. And it's not grateful that I can come back and share some of the life experiences. This topic is supposed to be very broad, so try to minimize too much technical details and skip over those. And those of you who are interested can always ask me at the end, or I'll be here tomorrow also. The existential threat to the human race is the global change. What is having? Did we have such a extreme weather condition, extreme climate change in the whole Earth's history? And answer is emphatic no. We never had within such a short period in the history of 4.6 billion years, over 200 years, so much changes have taken place. And there is a renewed emphasis focus on this particular topic. Obviously, I can only scratch the surface. So what I'm going to do is just to use some of the things and try to dive it to a level as in US commonly we say, the middle school student can understand. And there are some details I'll try to skip and move on. The single factor that is causing this change is population increase in human population. The population and human development due to excessive energy consumption affecting the food security is all the fundamental cause for this. So I'll show some data on human development, and then the case study will be Arctic where I spent a considerable amount of time in the Arctic. 10,000 years ago, the planet had 100 million people. 700 years ago, 400 million people. In 1800, 1 billion people. Now we have crossed the 3 billion mark. And that gives you some idea what is the population growth. I wish I gone as an econ and fascinated by this kind of data. This gives you data showing that 2 billion people were lifted out of poverty over a period of 25 years, from 1990 to 2015. The data, you can see it here, that you see the per capita here, the World Bank poverty line is in 1990, $1.01. In 2015, that reached $2. $1.90. These are like just with inflation, so we don't have to worry about inflation for sure on it. So now, in September 2022, 2.15 is the cutoff for poverty line. As you can see here, there is significant change over this. And you ask your parents or grandparents, how much maybe great grandparents, they will tell you how much they were struggling for food, how difficult their life was. The story is more or less the same, except very few people that going back to 3 generations, you are well off. So this is the fundamental reason of this global climate change, that all these have drastically changed on this planet. An example, quickly go over this. This is the one you might have seen elsewhere. This is one of the major accomplishments of the Chinese government. If you ask them what are the major milestones, they show this particular construction of the Three Gorges Dam as one of the great success stories. Here we see the human-made dams and reservoirs from all over the world has trapped 30% all river sediments. What is the implication? So you have less sediment going there, less nutrients carried by rivers and streams they are trapped in the impoundments. So that alters the ecosystem in the aquatic system, in the coastal area or continental shelf. Humans remove more soil and rock than all natural processes combined. Again, evidence of it. This is how one look at this data here. So what we are seeing here, 10,000 years ago, at the end of last glacial maximum, we had 57% of the forest in all the land. In 1900, we had 40% of the land was covered with forest. Now you see 38% is covered. Another extreme example is Haiti. In Haiti, over a period of 60 years, 99% of the forest is removed due to deforestation. So we have about 1% left. So there are many, many places that similar story continues here. What are the stressors? So all these changes results in what are the major issues? So these are some of those most important ones. The first one is global warming. I will go one by one, go over it. Ocean acidification, then global climate change that leads to flooding and drought. So the amount of water vapor evaporating from Earth's surface remains constant because the amount of solar radiation seen remains constant. The amount of water vapor that is in the atmosphere is supposed to remain constant, but what happens is because of surface ocean heating, more water evaporates and more water recycled faster. So when anytime water mass undergoes evaporation, the latent heat is transferred from ocean surface into the atmosphere. So the latent heat is released when it undergoes condensation, and that results in excessive rain, which is flooding, or deficient rain, which is drought. So this is all related to the hydraulic residence time of water in the atmosphere. That is the amount of water vapor that evaporates and how long it stays there. What kind of wind you have, the transport heat. Because of the wind pattern, it is redistributed, the heat is redistributed, resulting in flooding as well as drought. And that causes human misery. I don't have to tell you, a couple of years ago in Kerala, we could see several hundreds, thousands of people were affected. You saw the picture, and we are people we have never seen in our generation. This kind of thing, this story is very similar from all over the place because what is going on in other places. Then we have to increase the food production, to have food security, we use a lot of fertilizers. So the fertilizers are primarily nitrogen, phosphorus, potassium. So these are released. The nitrogen and phosphorus are nutrient element. So that results in nutrient washed off going into the coastal ocean. And if you put excessive nutrients, it's a feast for the fish and all these organisms, but they deplete the oxygen, it becomes anoxic. So when it becomes anoxic, then the chemical cycle is altered from oxic to anoxic. And you have massive harmful algal bloom formation taking place in the coastal areas. So if you go back to 1950, in the last 70 years, see how much the formation and sustenance of harmful algal bloom we see around the Indian waters, coastal waters, both in Arabian Sea and Bay of Bengal. There's an enormous amount of increase on that. So that's another issue. Then microplastic, as you know, that's another one. Now, all these agents increase in greenhouse gases, primarily carbon dioxide. So we are looking for ways to stay away from the hydrocarbon. Because hydrocarbon, you have no choice. The hydrogen and carbon, when you burn it, you extract the energy from the covalent bond energy, then it breaks down into compound and result in carbon dioxide. So to reduce our dependence on the carbon dioxide and other greenhouse gases, we are looking for wind energy, but that requires a large area with constant wind, which we don't get uniformly across this. This one shows the fertilizer use kilogram per hectare for the last 16 years in India. You see here in 1960, it's very close to less than something like 10 kilogram per hectare is the amount of fertilizer we use. Now here we are, you see, it has exceeded, far exceeded, and probably close to going to 200 kilogram per hectare. So all the green revolution that Professor M.S. Swaminathan instituted in 1960s, we became, selling global grains in the global market. All those self-sufficiency is all because of using one of the reasons is the fertilizers. This is the one you see the global production of plastics. Again, this shows the consumption of plastics. And you see here the curve going just like third curve, where you see here that microplastics. So you see that the one. And then this is on all the atmospheric, the pollutant, the gases that are released, reaches the atmosphere, and you have a very basic, if you want to know more about it, all you need for a week to go to Delhi, then you would know that it's basic. So we put a lot of pollutants in the air, and that affects our health. And again, this is all related to the human. All right. So here we are, the carbon dioxide concentration in the atmosphere. You see, it has increased about 51%. Currently, we have 421 ppm, and we started with 478 ppm in 1750. So we have the warming of air and ocean water, and the ocean acidification. I will show you a figure what really happened there. All right. So this one you see here, that temperature as you see here, this is the ice coverage in the Arctic. So we had close to 14 million square kilometers. So you are having that. Right. So here you see this one about 13, 14, somewhere around 13.8 square kilometer in the Arctic in 1980. Again, for 43 years, it has come down well below 13 million per kilometer. About 46% decrease we have. What is the implication of that? We will see to the Arctic, the ocean circulation and the heat transfer, surface water water on those two things. All right. To get some information about ice cover, 50 million years ago, there was no ice cap, either in the Arctic, there was no Greenland, there was no Antarctica ice cap, no Vasco ice cap. 40 million years ago, development of ice in Antarctica started to begin. 3 million years ago, the glaciation in the northern hemisphere. And the expected concentration, if everything was normal, is about 300 ppm now. This is the time when the beginning of industrialization with the advent of steam engine by James Watt. And carbon dioxide absorbs radiation instead of reflecting. And we have seen the average surface temperature of the Earth has increased by 1 degree Celsius. At that time, until 50 years ago, the global sea level rise was about 0.5 millimeter per year. Now, the average sea level rise is about 2 millimeters per year. So, as mentioned before, more evaporation, more heat transfer, leading to extreme weather events. This is common that we see, if you watch very closely, you can see this kind of extreme weather events. We have very pulsed, lot of rain falling in a very short period of time. So the frequency of the pulse events has significantly increased. We live in the Midwestern part of US. So from Chicago, it's about 4 hours by drive. We see now, this, for example, this last 2 months, we could see, we don't expect any cloud. And then 10-day forecast tells on July 30th, the chance of rain is 0%. The low temperature is this, high temperature is this. Then you check for the particular site in a particular source. I check in the iPhone. What is the low, high chances of precipitation? From 10 days from the day, the targeted date, that is 20th of July, I watched 20th, 21st, 22nd, and 23rd. There was so much singing. We never, at least I never saw that this kind of thing. So we are seeing very fast changes on this. So these are some of the figures that shows what I mentioned earlier, that in the last 25 years, from 1998 to 2022, 15 almost years for the past 23 years. Again, what I did. So all these point to that there is something going on that for sure it's beyond any question. This is one, the temperature anomaly, and how the temperature anomaly is increasing. You see that the way this curve is going, you can see that this increases like this. So with the high confidence level, we are seeing increase in global air and sea temperature. All right, next is ocean acidification. I try to break it down. This reaction is one of the most common chemical reactions. So you have the carbon dioxide. The carbon dioxide in the air, it combines with the water. you have precipitation, you have cloud condensation taking place. So that water combined with carbon dioxide forming an acid, carbonic acid. And that carbonic acid undergoes dissociation into bicarbonate and hydrogen ion. So hydrogen ion is just a proton, which is basically acid. Okay, that's how hydrogen ion concentration is imaged, right? So the bicarbonate dissociates into carbonate. So in this reaction, what happens is the more carbon dioxide in the top of the reaction that you have, so more carbonic acid is produced. So carbonic acid in the rain is brought down. That's why when you collect the rainwater, except it is not affected by industrial activity, you never get a pH of 7. So if you take and do a simple ninth grade calculation in chemistry, you will find out the pH of the water should be more like 5.6 because of carbonic acid coming from the atmosphere, assuming that no other industrial activity. We shut down all the industrial activity. So you have the pH of the water keeps increasing. And for example, in Indian Ocean, the pH in surface waters of the Indian Ocean is the lowest, 8.06 plus minus 0.03. In the southern Indian Ocean, the values are given here. So the surface pH of the Indian Ocean is the lowest among all ocean basins, and that impacts the corals and other carbonic compounds, shells, host shells, and all those. It affects that. So when we think this is not a big deal, and then look at it and say, yeah, we are finding this at the pH with a small change. Remember, hydrogen ion concentration, it's in log scale. So pH is equal to negative log of hydrogen ion concentration. So log scale difference of 0.1 corresponds to like 35%. So the acidity increases by 35%, or the hydrogen ion concentration increases by 35% for a pH change of 0.1. And almost we have a 0.1 as a result, 35% more hydrogen ion concentration we have in the surface water. What is the implication of that? And the implication of that is what we see here. So you see that the difference of 0.08. So 5.61, and that is yeah. Sorry, on the order. Anyway, you see here the shells that you are finding here. Yeah, this is the one. Sorry. So you see the rate of decrease, pH decrease you have here of decline by 0.08, and that is 26% of hydrogen ion concentration. So if we take the number of years from 1750 to now, you take the change, you can calculate the rate of pH decrease that corresponds to roughly 0.0014 to 0.0024 units. And the anthropogenic carbon dioxide, that is the fossil fuel combusted carbon dioxide, that has reached all the way to thousands in the ocean. So its impact is not only in the surface ocean, but it has penetrated all the way to 1,000 meters here. Now, if you go here, you see these shells, primarily in either calcium carbonate, either calcite or aragonite. Corals are mostly aragonite. So these shells become more translucent because the pH of the water increases, and that dissolves. As a result, you have thin carbonate shells because ocean is becoming more acidic. And thinner shells, possible disintegration, less protection against the predators. So these changes are all associated with it. The next one is a powerful algal dome. Some of these are, I will just try to show you a couple of things. So here you have this data, it's hard to read, but let me see if I can make it clear. So you have this blue color is the nitrogen. So this is nitrogen, and this is the phosphorus, and this one is the potassium. So these are the three nutrient elements you have in the fertilizer. So going back to 1968 and 65, this is 2020, you see this fertilizer use keeps increasing. And when this keeps increasing, obviously we say food production also increases, as you can see here. So the cereal production is increasing. This is for the last 10 years, how much it has increased. And this goes back to 1950 to 2012, the food production. So to feed the mouth of 1.4 billion people, we saw that we started with the population increase. So to feed this many billion people, we need to keep increasing fertilizers. And the fertilizers, we use these, some of these is washed off. The nitrogen and the phosphorus are washed off, and that leads to degradation of the water quality that you see. So this is another one where you find in here that this is all algal bloom. Sometimes you go to the ocean, coastal area, you have a massive fish kill. Normal, it's just normal water. So fish kill, you see it because there's a large amount of nutrients are discharged. So the biota, especially the phytoplankton, zooplankton, the necton, they get a lot of food, and suddenly there's not enough oxygen for fish to breathe. So without oxygen, once it becomes suboxic, below 3 milligrams per liter, then there is a mass death of fish. So the degradation is a result of excessive nutrients discharged from the watershed because we are using these nutrients in the water. All right. This is a one. This shows the number of algal bloom versus here you see the fertilizer used, and then number of red tides that you can see here. So the number of red tides increases with the increased use of fertilizer. So red tides is one of those algal bloom. There are different types of algal bloom. So you have that. So our fertilizer use to address the global population, to have food security, this is a kind of a vicious circle. You have more people, we have to get more food to feed them, and we need to use more fertilizer to get more degradation of the water quality. All right, this is a while ago, but I don't think we had this bad in little farther from our backyard. This is in Lake Erie, one of the 5 Great Lakes system. Here you see, suddenly there is a massive, complete, almost most of the Lake Erie was covered with a green bloom. And we do not see the surface water because these are all green blooms that we have like this. And this is one of the largest in the Great Lakes history. All right. The next one is biogeochemical changes in the Arctic. So this is the Arctic just to give you. Now we talked about the generic one. Now I'm going to take it specifically to the Arctic and show you what kind of changes we have experienced in the Arctic. To put some bearing where we are, here is the North Pole, and these are the watersheds. So you will say Lena River, Yangtze River, Ob, these are all Russian Arctic. And here you have Yukon, Mackenzie, this is Alaskan Arctic. So this is American Arctic. And this is the Russian Arctic. So we have done work here, collected samples and trying to identify the sources of radioactivity like plutonium, uranium, and all these ones to see whether this is coming from the dumped nuclear reactors from Russia and going back to 20 months and back. And so there is something very unique about the Arctic. The unique thing about Arctic is it has a very large river water flux. 10% of the global river water discharge is from Arctic. But the volume of the ocean is only 1% of the volume. Basically, we put a large amount of water, large amount of fresh water in the relatively small volume of seawater. The another thing, but there's something very unique about Arctic is ice rafting. Ice rafting is in the coastal area. You have in the early fall, you have a lot of snowstorm and the sediments get resuspended. So the superfine crystal of ice becomes what we call a fossil ice. These fossil ice, in the turbulence, it picks up large amounts of very fine sedimentary particles. Also associated radioactive substance that are constantly delivered from the atmospheric deposition. So we have massive amount of snowfall, and you have cold weather, lot of turbulence in the water, and atmospherically delivered radionucleus get enriched in this one. And once they are, these are called fossil ice with the sediments, and they travel from there to the interior of the Arctic. So we go to the Arctic, and in many, many places we see this one, and that is the one. To give you a little bit more about this Arctic, there is the Canadian Arctic or American Arctic, and the other one is the Eurasian Arctic. So the Eurasian Arctic is the water coming from through the France Strait. So France Strait, the Arctic waters come in. The Arctic waters from lower latitude, they enter through the France Strait. The water from the Pacific, they enter through the Canadian Arctic or through the Bering Strait. So this water comes here, this water comes here, the water mass undergoes circulation. And so if you take the Canadian side, we have a ridge system. Okay. So it's like kind of a bridge inside the water, there's a bridge. So water, the ridge, the depth of the ridge is probably about 1100 meters, but the basin may be 3,000, 4,000 meters. So you have this ridge, they have separated this laminar soft ridge that separates the Vyakhyaan basin from the Eurasian basin and so on. So this side we have two major basins, we have this side two major basins. All right. So the next one, little bit about albedo. So one of the defining characteristics of the Arctic is presence of ice-clapped sediments. We don't have it in the Antarctic because there is no river discharging in the Antarctic. In the Arctic, we have massive amount of sediment that is in the ice. For example, here, this is a dirty ice. So we collect the ice, bring it and melt it, and then allow filtration or gravitational settling and separation. We can separate the sediment and the water in this. And this is highly variable, varies from 8 grams to more than 250 grams in 1 square meter. Then you see here, this is the one we saw that before, the aerial ice cover has decreased significantly. Now, what is the role of this sea ice? Is this? The albedo of fresh snow is about 0.8. That means 80% of the incident radiation is reflected back. The albedo of the seawater is about 30%. That means 70% of the heat goes inside the water. The dirty ice or ice with sediment, it's also about 30–40%. So you yeah, if you have ice or snow, lot of light is incident is reflected back. If you remove those ice and snow, more heat is added to the surface ocean that results in warming. It's a simple concept. So this global warming is taking place in the Arctic because of the shrinking of ice. Shrinking of ice means aerial extent is shrinking, more area is exposed to sunlight, more heat is added to the ocean water. The surface water temperature increases. So it's a simple concept. All right. We are using some of the isotopes atmospherically delivered. That is, the last one is a cosmogenic isotope, which is basically produced from cosmic reaction. We have nitrogen, oxygen, argon, and other elements are there. So neutron from cosmos coming and hitting, you produce some radioactive isotopes. Berlin 7 is one of those. The latent polonium is coming in the uranium-238 series. Some of the work in these isotopes, the pioneering work was done by KFR/PRL, basically the same group that we have now. And that is, pioneered some of this work here. All right. So this is a one, to give you some little bit background about the Pluton is, you have the uranium-238, and the uranium-238 here in the rocks and minerals, some of it undergoes decay to produce radon. Radon is a noble gas, doesn't react with any other element, and it escapes. And so once it escapes and goes to the atmosphere, it undergoes radioactive decay, and it produces Pluton. So here we have Pluton. If it stays for a little longer, it decays to polonium-210. So if you collect the precipitation and measure the amount of polonium-210 and lead-210, we typically find 5% of polonium compared to lead-210. So the polonium to lead ratio is about 0.45. And if you leave, allow that to some time, that goes towards equilibrium, it becomes more and more until the activity of the parent, which is lead-210, and the activity of the daughter, this polonium-210, become equal. So this disequilibrium between the parent and daughter is what is used to determine the age of the rock or mineral. All right. So this is a one saw this here. And what happens if there is thermal warming? That shows we can potentially reach the ice-free Arctic. There are also there is a distinct possibility at the rate in which the ice is melting, both the perennial ice, that means ice that stays there year round, and the seasonal ice cover that may disappear. If they disappear, what could happen? Again, a problem. So if that disappears, what can happen is, this is what happened. You have much warming, then the polar amplification, and that will impact the thermohaline circulation of cold ocean. So warm water has a low density, all right? So cooler water has a higher density. And so this water undergoes sinking, and through long distance transport in deep waters, the heat can be transferred to other oceans in the Arctic and Atlantic from there. And that could affect the response. So that's the second one is the sediment dynamics from the coastal areas through the frozen ice. The sediment getting transported to farther away from the place of origin. That is a mechanism by which the sediments are redistributed. And the pollutants are also redistributed from this. You don't have to worry about the table. What this is all telling that we collected samples from the Arctic from 60 ° north all the way to 90 ° that is North Pole. We collected samples in the geotracers and we measured the polonium to lead ratio because that is needed in calculating the age. I will not get into all the details of the equation. Just to show you that we can date the snow. There is some snow sitting there. We collect it. We want to determine how many days ago how old this snow is. That's number one. Then number two, the sediments, ice-rafted sediment from the coastal areas is dispersed to faraway distances. We can determine the age of that. And the most interesting thing is the dating of melt pond. So melt pond in the Arctic is, let me see if I can show that. Okay, this is a melt pond. So most of them, even in summer, some areas of the Arctic is completely covered with snow, with the ice. So we need to have icebreaker to cut the ice and move. So normally if it is 50 nautical mile, 1.8 kilometer is 1 nautical mile. So when there is a thick ice, the speed of the ship drops to 3 knots. And so 3 knots versus 13 knots. And when this cuts and goes inside, we can see someplace there is a melt pond like it. Sometimes this can be half a meter thick, can be a meter thick. The aerial extent can be even small, the size of 1/4 of this room, the aerial extent. So what is happening is here you have snow, you have ice, and some seawater. So some of the snow melts, or all the snow melts, and that has a density of 1.00 fresh water, because there's a salt rejection mechanism in the ice. So some is derived from snow, some is derived from ice, and some is from diffusion from the seawater, which has a higher concentration of salt, potassium, magnesium, calcium, all those elements. So as a result, there is some diffusion. So each one has a characteristic signature in terms of density, in terms of the salt content, in terms of some of these radionuclides. So you have 3 equations, 3 unknowns. So you can determine the fractional input from these 3 sources. So when you do that, this is the one that shows the salinity of the melt pond. Seawater salinity, open ocean is about 35 per ml, 35 gram of salt in 1 liter of water. But here you see that is this is 4 grams per liter and the 6 grams per liter. In other words, here you have almost 100% pure water. But as you go deeper, you have more input from the seawater. So from this, we can calculate the age, how old it is, using the simple radioactive equation. All right. So these are the results. I don't want to get into all the detail. The mean ages of the aerosols is 12 days, and the snow is 13 days. Melt pond is 60 days, and the ice rafted sediment is 87 days. So the ice rafted sediment were found in the coastal area, but it is found in the deep interior of the Arctic. We know the distance. We know the time it has taken for this to travel from the dating of the ice rafted sediment. From that, we calculated what is the velocity, and this agrees fairly well with the satellite data we have on this. All right. This is just to show how much concentration is enriched in the sea ice, in the ice rafted sediment. You can see these numbers here that you have Retrutan concentration is about 300 dpm per gram. What does that mean? I mean, some of you will be familiar, others may not. What it means is 1 dpm is 1 atom decaying per minute is 1 dpm, disintegrations per minute. So here you see it's, you take the water and you remove all the Retrutan from that and compare it to what you have in the sediment. This is what you have. You know, this is 10 to the power of 6 cubic centimeter is 1,000 liters. So 1,000 liters of activity in seawater is what you find in 1 gram of sediment. So there's a lot of enrichment as this fine sedimentary material during turbulent period is scavenges, and that is why we have this enrichment. So we did say something in Lake Michigan, and we found even higher. We got one morning woke up and then contacted NSF saying that we want to do that. Within 6 hours, they said, go ahead. The American students are very adventurous. So I contacted them, and next day morning, 8 students showed up in the field trip, and we did that. All right, so this is a possible mechanism, all this. Now, I want to show you here what kind of changes we have seen, the changes that we found out from our studies. So here is one particular basin, Matra Basin, where the German scientists collected samples in 2007. We went back to the same station in 2015, 8 years after that, and collected and did exactly identical analysis. And then we can compare apple with apples. So what we are finding is this. The polonium 210 So when we collect a water sample, we take that, filter it through a filter paper, and the one that passes through the filter is called dissolved. One that is retained on the filter is particulate. So you wanted to see how much is in the particulate phase, how much is in the dissolved phase, the partitioning. So what we are finding here is this. When we compare 2007 data with 2015 data, the particulate polonium has increased by 26%. To give you the typical error associated with this, about 3%, 1 sigma. So even if we take a 2 sigma, that's 6%. So 26% clearly is different. So the Letrutan particulate phase, in over a period of 8 years, it has increased by 166%. If we take the whole water column, so the first two is in the upper 500 meters, and the whole water column, we are finding still significant difference that the polonium total activity, T stands for total, particulate plus dissolved is total, and that increased by 24%. And then the activity ratio also, because the activities change, the ratio also have changed. So that gives you some idea of what kind of changes on polonium. Now we look at the other data in the geotracers, part of geotracers, the European side, they have measured thorium dissolved, thorium-230 dissolved. And there also we find, so that you can see here, this is 2007, 2016. So the green color is 2007 data, and the 2015 is the blue color data. So you see clearly there's a distinct difference in the same site collected over 25 years, 1991, 2015. And the same thing with the dissolved and particulate. So this is a dissolved and one is a particulate, which is a thorium-234 particulate. And so this kind of change is common we are finding here. All right, I'm almost coming to the end. I have a bunch of pictures in the Arctic that we took. So I'd like to thank the taxpayers of the US, China, Turkey, India. You know, we are all funded by taxpayers of each nation, so we should be grateful. They would never know that we presented or the science they will understand, but we have a moral obligation because we are here because of them. All right. I thank the NSF Foundation, National Science Foundation for continuing supporting for a number of years. The last one is the one, the Great Lake, our St. Clair work, and then other collaborators and various researchers in different ships. Here we have, this is the geotracers work. This is Steadicam on the left, and this is, can you believe this? This is we had a massive snowstorm. The lake was completely covered. This is about 1,100 square kilometer surface area lake. Average depth is about 2 meters. So 100% was covered. The Americans will go on a car in the car, and sometimes they will go inside. And I would never venture to go on a lake and then on a car, and the car sinks, going to the bottom of the lake, where they do all. So this is the one. I think around 4 o'clock, I sent an email saying, "Hey guys, we need to go because if you miss that opportunity in 2 days, this whole ice will be, will be melt. So we won't be able to collect any snow." But we learned a really excellent lesson on the terrestrial ice mechanism, how the sediments get incorporated into that. So it was really fascinating. All right. Okay. These are some of the pioneers. Anybody can recognize left, the picture on left? Rama, yeah. His name is mysterious. Many people are asked, what is his first name? What is his middle name? What is his last name? They say Rama. But the first paper, he was the first one to measure Letrutan in the seawater when he was visiting strips. In the strips here, he collected in 1961, there was a paper in Nature. And so he was the pioneer on Letrutan in water. And then this is Lalsa passed away in 2012. And as my usual practice, whenever I go some workshops and this and that, I always go and see him. So this was my last trip to see him during the time. Let me see. I thought there was one another. I was on a cruise with a number of people. Uh, oh, that's all. Okay. Questions?
Very much work already is talking and bring us into the architect. The part is open for the questions. Anybody have any questions?
Yes, sir. Also, but
So your teacher have a question.
oh yeah, yeah.
Old habit of mine of asking questions. I was wondering if you can, in one of your later lectures, superpose. You have a figure which shows the rise in the consumption of fertilizers.
Yeah.
So on that, you can superpose the rise in the population.
Oh yeah, yeah. That's a good idea. Yeah, yeah. People can connect it. Yeah, that's true. Yeah.
That was.
All right. Excellent idea. Yeah, I will.
Sir, you explained that because of dirty snow, the albedo is getting down. So can you explain how humans have contributed to more sediment going towards Arctic?
Okay. Yeah, yeah. That's a great question. So what happens is 36% of the Arctic is shallow water. So what we call, I'm sure many of you know what is a continental shelf, continental slope, but there are some physicists. I was once upon a time a physicist. We didn't know what is continental shelf slope. So the continental shelf. So what happens is when there is this ice or snow, the wind will not affect, and that will result in resuspension, the shallow water sediments. But when you remove the cover, ice cover, then the massive snowstorm time that will undergo resuspension. So that results in high particle concentration. As the particle concentration travels without the hindrance of ice cover, on the way it picks up more particle reactive isotopes. So often it's the particle reactive nature of the particular isotope that results in the scavenging, and that is because of ice-free cover you have.
So in one of your slides, you showed that you calculated the resistance time of aerosol using lead to 10 and polonium to 10. And the values I saw 13 plus minus 11 or similar to that. So is there any way we can reduce the plus minus value there?
Oh, okay, okay. That error is the error on the data, error on the standard deviation on the data. It is not. It's not the propagated error on counting statistics and blanks and standard and all that. That we can have a control much lower, 5-10%. Number one. Number two, the aerosols in the Arctic has a very low concentration, but the quartz filter we use to collect sample has an inherently higher background.
What I was asking, it is 13 plus minus 11 days.
Right, right,
It is somewhere between 2 days to, if you are going up to 24 days.
right.
That value I was thinking, 13 plus minus, we can say 2 days or 3 days, between shorter.
Right. So what that tells, you have 13 data points. The range in the 13 data points is very high. See, for example, you get a 4 days. You have 25 days. So when you have like this, you take a standard deviation on the error, you get a much higher error. And that's what I'm saying. When you say the data, it is not the counting statistics error. It is the scatter in the data. And we have no control over that. Because this is a geotraces cruise. So they collected, there was a group, aerosol group, they collected samples for everyone. So they said, okay, for you, you get a 2 slice of 160 cubic meter. We didn't have a choice asking for collecting our own, 1,300 cubic meter of volume, collect for 2 days. No, within the time constraint, we have the tissue. Yeah.
One more thing.
Yeah.
You are saying this is the residence time of aerosol.
Yeah.
And we know that aerosol size ranges a lot.
Yeah.
And
PM10.
It's are particle reactive and they get attached to the aerosol particle.
Yeah.
The surface area of particles is changing with respect to size.
Yeah.
That means if we are doing bulk, you can be highly biased.
Yeah.
So is there any way to take care of that?
This is basically all the particle below 10 micrometer, PM10. Yeah.
But there's a huge range.
Yeah.
Starting from few nanometers up to.
Sure. So it's basically a composite. We did not have the luxury of designing our own, size fractionated aerosol, like what you see in the cascade impactor, for example. You say 6 sizes. If I'm doing it my own, I have my own funding, I can do all that. But here is a joint effort as a part of the geotracers, and they all have their own stuff. So yeah.
So that means that resistance time can be biased depending on the size distribution of aerosol collected on that PM10.
It's possible, but we basically said our aerosol definition here for this particular study is all that is collected in one size less than 10 micron. Yeah. Yeah.
I want to go talk about that, the figures which you have given.
Yeah.
About the rise in the increase in the population.
Yeah.
When you go back to many thousands of years.
Yeah.
What is the source of the data for that?
Awesome. Right.
It's just working back from present, right?
I think I really do not know how they get this data. My guess is based on certain types of fossils, and there may be a lot of extrapolation. They came up with the data. When there is no other better way of taking it, somebody gives the number, we say, okay, how good this data is, I don't know.
I would guess that just taking from the last 100 years.
Yeah.
It looks exponential.
Yeah.
And just extrapolate backwards.
It's possible. I mean, the two things is life expectancy until they discovered antibiotic is much lower, number one.
But the rate of human growth after never was processed. So,
Yeah.
You know, how to produce nitrogen.
Mhm.
And,
All right.
okay.
Thank you for the nice talk, sir.
Thank you.
So actually, you showed a lot of evidence for climate change and many different types of indicators for that. But like your former president, Donald Trump, believed that it was a hoax, and he just pulled out of the Paris Climate Accords. And now the forerunners in the Republican presidential candidates, most of them believe that climate change is actually not very serious, and they in fact say that it's basically hampering the US economy. They're saying that the growth is affected by this. So they want to just start using fossil fuels again, and they want to increase the economic growth by doing this. So what is your comment on this? What is the basis for their claim that this is a hoax, and what is your comment on this in general?
All politicians in the globe, it's all about preservation. They want to think about the next election and all that. Republican, in the heart of hearts, they know that what kind of climate change is taking place. If there's one senator in Virginia, for example, and he would not talk anything, he's a Democrat, anything he would not talk about fossil fuel. Because if he says anything from West Virginia, it's a highly red state, Republican state. He will never get re-elected. So it is all about, their political future. So that's number one. That's the most important. The second one, there's a senator from Montana, and 80% of the revenue comes from oil-related, mineral-related industry. If he says any supports any regulation, forget about it, he'll never get re-elected. He or she will never get re-elected because their economy crucially depends on that. So this kind of a politics plays a major role. It is not their heart is saying that we speak it out because we are scientists. We want to be objective as possible. The politicians are all about, their preservation. That's the reason.
Anyone else has a question? Okay.
I would love to hear more from the students, our future. Maybe you can tell your name and what year you are a student. I would love to hear that.
I am Ashish Tanay. I am a summer intern student. So my question is, first question is why the surface water pH of Indian Ocean is very less comparatively to the other oceans. Is there any specific reason for that? And another thing is the hydrocarbon use of hydrocarbon as a fuel? Does it really impact the pollution? Because there are a lot of petrochemical products other than the energy. Like we are more focused about the hydrocarbons as used as the energy we should reduce that. But there are a lot of co-products like tires and homeopathic medicines and other things like construction works. So we need hydrocarbons for that use also. So are we only biased on the use of hydrocarbons for energy that is leading to the pollution, or it might be other things also?
Yeah. Yeah, right. That's really good. First one about this way, the Indian Ocean difference. It could the carbon dioxide. If you put carbon dioxide, it mixes very uniformly in about 2 weeks' time. So I don't think there is the carbon dioxide concentration is going to be very different. On the other hand, if you have some regional industries, maybe Asian Pacific or not Asian Pacific, let's say Australia or some of the countries with the, adjoining the Southern Indian Ocean, if they have some, that could be local. The industry releases a significant fraction is brought down by precipitation. So you may have some higher amount. I really do not know. That's a possibility. The second one, fossil fuel versus non-fossil fuel contribution to CO2. Yes, manufacturing cement, everything that we make, there is some energy involved. And that energy can be from one form to another to convert. We are not saying it's all, everything is coming from fossil fuel. However, the fractional contribution from each of these sources clearly tells the hydrocarbon is the major source. Not necessarily hydrocarbon per se, we take our car and we drive, so that is released. Or, the palm that we use to heat or cook our food, that is a natural gas, that's a carbon dioxide. But there are various other forms, but these are the major. So when we talk about things like this, it's the fractional contribution to carbon dioxide, which is the major one, which is fossil fuel combustion.
Hello, sir. I'm Sanadika, research scholar in Geoscience Division. So my question is regarding the global average temperature rise, the plot you have shown. So there is a clear cooling, global cooling from around 1940s and 40s to 1970s. So I have read in some paper that it is because of the aerosol, the sulfate emitted because of the World War II. And in some papers, a controversial statement that it is because of the lack of measurement or because of changing of the instrument. So I want to know about your comment on that.
Yeah, I mean, analytical methodology keeps changing. And previously, like QA, QC, analytical
quality control was not emphasized, like intercalibration or standard reference material to measure some parameter were not that prevalent. In 1940s, I don't know whether NIST or previously it used to be NBS, National Bureau of Standards. So the question is the quality of data. The quality of data that needs to be, so if I make a measurement and say my data is the best and this and that is one thing, but my data is validated with the standard so that no, my data is comparable to any other lab because I used a certified standard. So this is the one thing I always teach, emphasize, saying that what is the most important thing to get a high quality data? Tomorrow students go for working in consulting company and they must care about the data, which means they need to first do a certified material in their lab to get the data right. And those things are not emphasized. I really do not know what percentage we can account to that. And also there's no way of going back because I just working on a paper, I submitted to this reviewing 60 years of data on the polonium lead and people got away with murder. You say, how did they do it? This is from Yale. This is from, this guy in, Tokyo, a very prominent lab. And they're all gone now. But the point is, data quality is regulation. So I do not know this 1940, you are saying the cooling, whether it is reported by universally people have reported. Because those data, there was no data repository to go back. In carbon dioxide concentration, Charles Keeling started in 1956. And so, that guy spent his whole life on that. And so there is a high quality data control on carbon dioxide from 1956. So before that, you say, how about before? We don't know whether the data is reliable or not. Yes.
So it looks like we do not have any questions. So I have just one broader question for you because you have worked in Arctic. So biogeochemically, if you are to answer, what is the difference between Arctic and Antarctica fossil? And what are the major points one should kind of look?
Okay, one major difference between Arctic and Antarctica is you have no sediments discharged into the Antarctica. There is no major river discharge into Antarctica. So riverine sediment going and getting transported into the interior is not there. So that is the one big difference. The freshwater input from ice during melting season is much higher in the Antarctica compared to Arctic. That is another one. The third one is there are some atmospheric transport is taking place. We are finding it much higher concentrations in Antarctica, like for example, the Teuton fallout at radon. We are finding suddenly radon increases by 2 orders of magnitude, what we call radonic storm. It was not noticed by the scientific community, but when I was writing the book, I found out. Question I'm asking, scratching my head, saying that where from this is coming, whether it is coming through these atmospheric rivers, where you have massive amount of water vapor is going along with somewhere radon gets funneled and it gets carried away. I don't know. So there are distinct issues with respect to the melting of sea ice contribution. Antarctica is basically land, right? So on the land mass, you have massive amount of ice. Then we have Lake Baikal. Underneath Vostok, we have lake, where there is a solid, even in the cold environment, you have such a vibrant and biological community. So that's another one. This kind of ridge system, I don't think you have ridge system in the Southern Ocean, as we have very prevalent, distinct ridge system, with 4 major ridges, which basically constrain the water mass circulation or water mass flow. That's another one.
Thank you very much. So now I request our director, Professor Anil Bhardwaj, to
Get it with a souvenir.
Oh,
So.
yeah. I was here for 50th, and there are some fantastic scientists had come. Some of them the best in the world. Jerry Wasserberg. PRL tried to invite him for many long. These people were so occupied with their science. And so, but at the time, John Edmund from MIT, Wasserberg from Caltech, Keith Onions from UK. There were 4, 5, 6 National Science Academy members from US, and that's not a joke. And so, you know, now here I am in 75th. I'm so delighted to be here.
So now I invite my colleague, Dr. Bindu Swami for vote of thanks.
So friends, we have reached the conclusion of a very interesting session. And first of all, we would like to thank Professor Mark Baskaran for visiting PRL and giving an excellent talk in PRL Ka Amrit Vyakhyaan, or rather 82nd episode of the series. And I would also like to thank you for taking the audience's questions so nicely. And thank you very much, everybody, for coming for the talk. So I would like to thank all the audiences in this hall who are present in this hall, and also who are watching our PRL Kamrit Vyakhyaan through the online mode. Next, I would like to thank Professor Anil Bhardwaj, Director PRL, for his constant motivation and encouragement to carry on with these events. And so far, we have made quite a journey with 82 episodes so far. I would also like to thank Registrar PRL, Professor R.D. Deshpande, and Dean Professor D. Pallam Raju for all their efforts. And I would like to thank Chair PRL Kamrit Vyakhyaan Committee, Professor Nandita Srivastava for organizing the event, and also all the members of the PRL Kamrit Vyakhyaan Committee for all of their efforts. And so we'll be continuing with these events. So for PRL Kamrit Vyakhyaan series, so do visit PRL website and other social media platforms to know more about PRL Kamrit Vyakhyaan, as well as other events being held at PRL. And with these words, I would like to propose for the closure of today's session. Thank you very much, everybody.